Alright, now we're coming to series. And series is a lot of fun because it's actually the summation of a sequence. Okay. Now this is an arithmetic sequence, so an arithmetic series is an arithmetic sequence. Okay, so that's exactly what a series is going to be. Okay, now a finite series, if you think about it, our sequences went on forever. You can continue the pattern forever. You can find any number in that sequence and just work with it. But a finite series, in which you're adding up all the numbers, we can do. An infinite arithmetic series we cannot do. So cannot do an infinite arithmetic sequence. Because you know what? They're going to, because they all diverge to infinity. Okay? So they all go up to infinity. They don't converge on one number. And we'll learn more about convergence in the next video, but for right now, we can do lovely finite series, but we cannot do lovely infinite series. Or at least we cannot do infinite arithmetic series, which should be, dun dun dun, a spoiler for geometric. Okay, so limits. Limits are what I'm talking about with divergence. If I add up enough numbers enough times, I'm going to get close to infinity. If I subtract enough numbers enough times, all the way up to an infinite amount of times, I'm going to actually go to negative infinity. So when we're talking about the limits here of an infinite series and infinite arithmetic series, they won't be approaching any certain one number. Okay? And series is just pretty simple, what we just talked about. Now there are ways of writing certain series. For example, if we wanted to write an arithmetic series, we could do this. Okay, another way to write a series is actually looking like this, where you actually have a summation symbol, which is sigma. You have the starting number, n equals 1 down here, and going up to n equals 5 up here. So what this actually means is 4 times 1 plus 4 times 2 plus 4 times 3 plus 4 times 4 plus 4 times 5. And then you would actually solve that sum. And so that would be 4 plus 8 plus 12 plus 16 plus 20. Okay. And you could actually derive a lot of information from that. As a matter of fact, this right here isn't your constant ratio, or your common ratio, it's actually your constant difference, your common difference. Okay, so you could actually derive a lot of things. So like for example, your first term, you can derive from this by using this formula. Okay, your first term would be 4, pretty simple, we calculated that in the beginning. Your fifth term would actually be 20, and your common difference would actually be 4 just by looking at that number in front. Okay, now why is that useful? Because sometimes that's all the information you're given and you have to find the sum of a finite arithmetic series. Now you could add up all these numbers and do that, but what if this had been instead 50? Holy shnikes, now this number is no longer useful. You actually have to find the other numbers. Okay, so you're going to have to do a lot of other different things. You could still use the a sub 1 is 4 and the d equals 4, but then trying to add it up by yourself is just going to become more ridiculous. So that's where the sum of a finite arithmetic series formula came from. And there are some, there's an old urban myth that Euler actually figured this out. And he said one day in class he was sitting there and the math teacher, like usual, was the dumbest one in the room. And that's definitely true when I'm teaching. Okay, but the sum of the first, Euler was already done with his assignment, so the teacher said, to the rest of the class, he said, well, guys, let's go ahead and try this one. I want some busy work. Let's find the sum of the first 100 numbers, counting 1 plus 2 all the way up to 100. And they sat down and did it, and Euler sat there and looked at the problem and kind of manipulated it, and then he turned it around and he actually said, you know what, I actually found it, here it is. And he said it was 5,050, and the teacher said, whoa, how did you get 5,050? That's pretty fast. And the teacher, once again, rumor, this is why these urban myths, I don't like them, because they always put the math teacher as the dumbest one in the room, even though it's actually sometimes true, like myself. But for example, on this one, what he did was he took a look at the information. So he took 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus plus 97 plus 98 plus 99 plus 100. And there's a good reason why I didn't do that. So what he did was he said, you know what? Here's an interesting concept. Okay? 99 and 1 make 100. 98 and 2 make another 100. 97 and 3, 96 and 4, 95 and 5, 94 and 6, all the way down. Now, obviously, there's going to be one odd left number, which is just the plus 50 here. Okay, so you're not going to pair that up with anything. But he noticed that there was, let me see, there was 49 pairs of numbers that actually added up to 100. So what he did was he did 49 times 100. Okay, then he added the extra 100, and then he added the 50. And that's how he got 5,050. Okay, and obviously he got the ruler for that one and stuff. But in actuality, it's actually what we've learned about before is that if you take a series or a sequence and you kind of rearrange it to look for patterns, you're going to actually come up with some surprising formulas. And this was actually one of them. Okay, in which you take, this is the actual result. You take the number of terms, you times it by the first term plus the last term, and then you divide it by 2. Okay, alright, and so for this sequence of Euler's sequence, it's going to be 100 terms times 1 plus 100. Okay, and then we are going to divide that by 2. Okay, and if we actually take a look at that, 100 times 101 divided by 2, and that turns into 50/50. Okay, which works out the same way that Euler did, except in a nicer, neat formula. Okay. So, once again, to be thankful for the sum of the first n terms, the best, right here. Okay. Now, like in the past videos, you can solve this for the sum of the first n terms variable. You could solve it for n, or the first term, or the last term variable. So let's take a look at some of those. Alright, so first off, we'll find the sum of the first 12 positive integers, even numbers. Okay, so if you're taking a look at this, this is 2, 4, 6, 8, ... It just keeps going. Okay, so you might need to use a combination of a couple of elements. So I'm going to find the 12th number. Okay, and I know this is an arithmetic sequence. I do know that the first term is going to be 2 plus 12 minus 1 times 2 is going to be the common difference, obviously. Okay, so this becomes 2 plus 11 times 2 is 22. So this is going to equal 24. So that's the 12th term. Okay, so and then in order to use my summation part, I would do sum of the first 12 equals, let me see, 12 times 2 plus 24. Okay, and then I'm going to divide that by 2. Okay, so that's going to be 12 times 26. 312 divided by 2. Okay, and then we just divide that by 2. And the sum of the first 12 numbers is actually going to be 156. Okay. Now, the sum of the first 75 numbers is 282,850, and the first and last terms are 1 and a sub n respectively. Find a sub n. So in other words, this one you're going to be doing 285 equals 75 times 1 plus a sub n divided by 2. And as you can see on this one, we will be timesing both sides by 2 first. Okay, so we go 2850 times 2 is going to be 5700 equals 75 times 1 plus a sub n. Okay, we divide that by 75. And that actually gets us 76 equals 1 plus a sub n, which should actually turn into 75 is the nth term of this sequence. Okay, a sub n. All right. Okay, so an actual application problem. A theater has 60 seats in first row, 68 in second, 76 in third, and so on and so on. If the theater has 20 rows of seats, how many seats are in the theater? So you have to find the 20th row first to find out how many in there, and then you actually do the actual sum. So the sum of the first 20 rows is going to be 20 times 60 plus 212, and then we're going to divide that by the magical 2. And that's going to turn into 2,720 total seats in that theater. Okay, now how many terms of the arithmetic series -3 to 7 must be added together for the sum of the series to be 116? So here's the formula set up. I don't know the last term. I don't know the number of terms, so I actually have to replace. What I'm going to do is I'm going to get this all in terms of n. Okay, so I'm going to come up with the formula for n and then plug it in for a. Okay, so now that I know that a sub n is n, well, first off I distribute the 5 and then I combine the -3 and the -5 and I get -8, so I'm going to go ahead and plug that in. So this is going to look like this. Okay, the good thing is that we know that when all set up it's going to look like this, but we know that this is going to turn into 116. And then we can times that by 2. Okay, and so now it's going to be 232. So we know that that's going to be 232. And then when we distribute the n, it should look like, okay, so it's going to look like this. And then what I'm going to do is I'm going to rearrange it in true quadratic formula. I'm going to have 0 equal, well actually, yeah, I'm going to add everything to the left. Well, no, I want the 5n to be positive. So it's going to be 5n squared. I'm going to rearrange everything. Minus 11n minus 232 equals 0. And then I'm going to do the quadratic formula on that, or I can actually factor that. And if I actually work with it that way, I should factor it to be 5n plus 29 n minus 8 equals 0. Okay, and as you can see, only one of those is truly going to be an answer. If you use the quadratic formula, I'm not going to blame you or anything. But the number of times you must add up, the number of terms you must add up in that sequence to get 116 is 8 of them in that sequence. Or you could do the old-fashioned way of figuring it out and trying to get to a summation of 116. So you could add it each time and just see how far you're getting. Okay, but that's it for arithmetic sequence. I'll talk to you guys later. Bye.